Today, let's talk about Gaussian process regression. Gaussian process regression extends the kernel ridge regression as a Bayesian inference framework. In kernel ridge regression, we can obtain a fitted curve using the kernel tricks. The Gaussian processes takes one more step on that not only give us a fitted curve, but also give us a posterior distribution over the fitted functions. It uses the idea of the Bayesian interpretation for the ridge regression problem, where the ridge regression estimate becomes the posterior mean for the Gaussian process regression. So this is the same as the kernel ridge regression, but in addition to that, we also have a posterior distribution with the uncertainty term associated with the curve. That is really the power of the Gaussian process. To understand how Gaussian process regression works, let's first take a look at how we can use the Bayesian framework to understand the ridge regression problem. So let's consider the finite dimensional ridge regression problem. So we can actually set up a probabilistic framework for it, not just as an optimization problem. So here is a problem setup. So we have ridge regression as a Bayesian model. So first we're gonna look at the finite dimension version, but later we're gonna translate this into the infinite dimensional version. The whole mathematical derivation just carries out because we have the same linear algebra structure for the function space. So as soon as we work through the finite dimension, we see that the exact same form will show up for the infinite dimension problems. So this is a model we'd like to consider that yi equals to f of xi plus epsilon I, where the fxi, let's just write it out as a nonlinear function with a finite feature map phi of xi transpose beta. And here we want to consider everything into a probabilistic framework. So we want to assume a distribution for the epsilon. So epsilon is a noise that distributed as a normal of 0 sigma square. Then in the Bayesian model, the beta, our parameter, will have a prior distribution. So let's say that beta distributed at beta 0, then tau square, right? So that's the variance of it. It's still going to be a normal distribution. And then, so the goal of this inference problem is that we want to estimate the posterior for the beta. So the goal, let me say, the goal is the posterior of beta. And actually, to make a tighter connection with the infinite dimension case, let's just do the posterior of f instead, right? Because they are linked. So in this case that phi is not random. I should say that in here that epsilon and beta are random. Phi is not random. This phi here is not random. It's fixed. Okay, then our f and y will also be random, right? So this is f is random, y is random. The only non-random thing is phi. So because beta and f are linked, so the goal will become estimate the posterior of f of x. So that is the goal. Okay, now let's just write down the base rule first. So we have the probability of f of x given y equals to the probability of y given f of x times the prior distribution of f of x over the probability of y. So that's the base rule. And then to just make our derivation a little easier, let me just write down the vector and matrix form for the variables. So so first we will have the epsilon. So that's going to be an n by 1 vector that distributed as normal 0 sigma square I. Then for the beta, that's going to be a vector. So it depends on our the dimension of the feature space. Let's say it's m dimension. That's m by one vector. It's going to be normally distributed as beta 0, then tau square I. I'm missing an I in here because beta is a vector. The next, we'll have the phi matrix. So the phi matrix will have all the data points. It's going to be an n by m matrix. That will be the phi x1 transpose all the way to phi xn transpose. Then we'll have the f vector. So the f vector will be the n by 1 vector that has all the evaluation point from fx1 to fxn. Then because we are scaling the normal distribution with a constant, so the f will also be a normal distribution, will be a multivariate normal. So the mean of that will just be phi times beta 0. Then the variance will be so this is a property of the Gaussian distribution will be tau square phi transpose. Okay, then you'll see here that the phi transpose is going to be the kernel matrix K, right? So that equals to kernel matrix K. And let me just call the mean of this to be F0. So that's going to simplify our algebra later on. So that equals to the normal distribution of F0, then tau square K. So that's the distribution of F. Then we'll also have the Y vector, right? So Y vector is going to have just going to be y1 to yn, right? So that's also going to be a normal distribution, right? Because here we are summing two normal distribution, then that means y is also going to be a normal distribution, right? So that's going to be a normal with mean f0, and then we just sum the variance together because we assume that the beta and epsilon are independent. So I should write here that beta is independent of epsilon. Then we can sum the variance together to be tau square k plus sigma square I. So that's the y vector. So now we have everything written down in the vector form. So this is everything written down. And then let's apply the Bayesian inference to see what we got, right? So let's just plug in everything into the Bayes rule to see what happens. So we have the okay. So see here, the next thing is that everything is multivariate normal. So in fact, we can just apply the property of the multivariate normal distribution without plugging the numbers into the Bayes rule. So that's super nice. So let me just say the property of the normal we're going to use of normal is that y is normal, then f is normal. That means the joint of y and f are normal. Then the posterior, the conditional distribution, for f given y and y given f, right? Everything is normal. So that's the property we can directly apply in here without even using the Bayes rule. Okay, so the next thing I can do is that I can just write down the joint distribution between y and f. So we can write down the joint of y and f. So that's going to give us, so this is going to be a 2n times 1 vector, right? Okay, so we'll have the vector y and f. Let's just concatenate them together. That will be a 2n times 1 vector. It will be normally distributed. So the mean of this will just be f0 and then f0, right? So that's going to be the mean. And then the variance for this will be, let's just write out the diagonal first, right? So here we'll have tau square k plus sigma square I, and then the other one will be tau square k. So the off diagonal is the covariance between y and f. So let's do that. So the covariance, you can just compute that. So y and f, that equals to the expectation of y f transpose minus uh, the expected value of y times the expected value of f transpose. Okay, so here we can actually replace y with f plus epsilon, right? So then we can just expand the terms as expected value of f transpose plus epsilon f transpose. Then the expected value of y is the same as the expected value of f, right? So you can see from here, right? So it's the same as f0 as the expected value of f. So that's going to give us the expected value of f e f transpose. Then for the first term here, we can actually separate all the two terms, right? We have the value of f transpose minus expectation of f expectation of f transpose. So that will give us the variance, right? So this becomes the variance of f. Then we also have plus expected value of epsilon epsilon times f transpose. So for the second term here, because epsilon and f are independent, right? They are independent, so that means we can factor them. That means this term here equals to expected value of epsilon times e of f transpose, right? Then this whole term goes away because the expected value for epsilon is 0. So this just gonna give us the so this whole thing here just gonna give us a variance of f that equals to tau squared times k. Okay, so now we can fill in the matrix. So we'll have tau squared times k for the off diagonal block matrices for our covariance matrix. So this is the expression of the joint distribution. So that's gonna be a multivariate normal, right? Then we can actually just directly apply the property of the Gaussian distribution to write down the conditional distribution for it. So for the multivariate normal distribution, we have this property about the conditional distribution being normal. So suppose that we have two vector A and B that distributed in this way. So we have the corresponding mean and variance term for both A and B, as well as their covariance. Then the conditional distribution of B given A can be written down in this way, right? So that's also going to be a normal distribution. It is a fact that we can directly apply for our problem here, right? Because we want the posterior. So the posterior, then we'll have f given y as a normal distribution of we just plug in the numbers here. So f0 plus tau square k, you have an inverse term, tau square k plus sigma square I inverse, and then we'll have y minus mu a will be f0. So that's the mean term, and then we'll have the variance term as tau square k minus Okay, so that's the final form you have in the end. So let's just do a few simplifications for this, and we'll see the kernel ridge regression is there. So the first thing that we can do is just to set f0 equals to 0, right? So that's then the next thing that we can do is just to move this tau square term inside, right? Because we have an inverse in here, that's gonna cancel with the tau square. So what we're gonna get is just gonna be k times k plus uh, sigma square over tau square I inverse, and then we'll have y. Okay, so this is the exact same formula as the kernel ridge regression. When if we just replace this value here with lambda, right? If we just set this to lambda, then that's the exact same formula as the kernel ridge. Uh, the next term we will have the is that it's gonna be all right. Let me just divide the tau square term again. So actually, let me just move this tau. Let me just take out one tau square term outside, and then we'll have k minus, and then k times k plus sigma square tau square, and then I'll have I inverse k. Right, I believe this is a variance formula for it. And then we can set this into lambda, right? So see lambda in here as well. Now, this is a very nice formula, right? So we get the exact formula for the kernel ridge regression as a posterior mean. So this is a posterior mean. Uh, posterior, that's what we usually use as the point estimate for the Bayesian problem, for Bayesian model, right? This is a posterior mean. It's the same as the KRR formula, right? KRR formula. So, but not only we have mean, right? We also have the variance for the curve fitting, right? It means that we are not fitting just one curve, but we fit a distribution of the curves. We have the uncertainties of the curves. That's really the power for this Bayesian interpretation. So now the thing is that we want to translate this into infinite dimension space, but you see that the equation will look identical to this one, right? This we can just in fact just write it down as the exact formula. So let's do that. Okay, so here's a problem setup, right? We'll have the data point xi and yi for I goes from 1 to n. Now let's just directly consider the model as yi equals to f of xi plus epsilon I. So here that the difference is that f, we directly model that as a function that goes from Rd to R. Right, so we want to kind of avoid writing it out as phi transpose beta. So that's the only thing changed. So now for the prior distribution of f, prior distribution f is because now we have a function, right? So we're just gonna directly assume that to be a Gaussian process. It's like a multivariate Gaussian, but in infinite dimension. So we'll have function f0 as mean, and then for the covariance that will be k x x. Okay, so for this Gaussian process, how do we interpret them? Is that suppose we are given fixed data points, right? The evaluation point. So the evaluation point, suppose we have x1 to xn, then we can obtain a finite vector from it, right? From fx1 to fxn. So if we do that, then everything reduces to our finite version as multivariate normal. So it will just reduce to f0. Now this is a finite vector. So let me just write a bar on top of it, and then our matrix K. So everything reduces to a multivariate Gaussian when we add the evaluation point for this function f. Okay, so that's a nice way to think about the Gaussian process. And then we also have the noise term, right? So let's continue. We have the noise. So epsilon, and that's gonna be a finite vector, right? That lives in Rn. So it will just be 0 and then sigma square I. So for our y, vector here, right? So y is going to be the normally distributed because y is also finite. So we'll have the same equation as the finite version of it. We'll have k plus sigma square I for the y vector. Okay, so now for the joint distribution of y and f, we can write that out directly. So here, let's just do things a little bit different. So instead of the function f, let's just take out one particular evaluation point x star, right? So that's gonna be a multivariate Gaussian, right? So we just take out one particular evaluation point from it. So it will have the mean of f0 and then f0 of x star. And then the variance of that will be the first term is the same. It's going to be k plus sigma square I. Then in here we'll have k x star, and then we'll have k x star x, and then k x star x star. Right? So that's going to be the joint distribution between y and any evaluation point x star. Okay, then for the posterior distribution, we can just write it out directly. So the posterior, so we'll have f of x star given y, that is a normal distributed distributed as f0 of x star plus k x star, and then you'll have k plus sigma square I inverse y minus f0. So that's going to be the mean. And then for the variance, we'll have k x star minus k x star x, and then I'll have the k plus sigma square I inverse k x star. Okay, so that is the full posterior distribution for our estimate, right? For function f, right? For whatever, for each evaluation point, we will have a Gaussian distribution of it. So that is a Gaussian process regression. Okay, so now let's think about how we can use this problem to perform statistical inference, because it's not just going to give us a point estimate, it becomes an inference model for it. So this is a posterior mean, right? So if we want to obtain a point estimate, we can just use a posterior mean for it. So use a different color. We have the posterior mean. Right, I'm not going to copy the term again, right? So that this is going to be the term. If we want to obtain a point estimate of it, of the function. Now we can also think about how can we use this uncertainty term here. Then the other interesting thing, right, it's about the other interesting change about the interpretation is that you see this K matrix here. You see that our choice of the kernel matrix here, that becomes a prior of the problem, right? So I should say that the prior is the choice of the kernel K. Right, depend on different function we choose, we are basically using that as a different prior for this Bayesian inference problem. Then we also, because this uncertainty term here, the variance, we can also perform statistical inference using it, right? So we can also do inference. So for example, we can do the credible interval for the Bayesian models. That is usually defined as mu minus 1.96 sigma to mu plus 1.96 sigma, right? So that is the interval. You can just we can just plug in the formula for the mean and variance into this equation to get a credible interval for the curve, right? So that's a way to quantify the uncertainty. Also, we can do the hypothesis testing with it, right? So hypothesis. Okay, actually, we are in Bayesian framework, so I shouldn't say hypothesis testing. So we can compute this. We can compute the probability of fx star greater than 0, right? So that is something we can also compute because we have a normal distribution for it. We can that's something we can compute, right, as a kind of observation version for the hypothesis testing. So that's pretty much what I want to say about the Gaussian process regression. So comparing to the kernel ridge and the smoothing span, you see that here we are assuming we have a full statistical model, probability model, where we have the distribution for every parameter of it. That's very powerful, right? Because for the smoothing span, we just have one objective and then solve that objective to fit a curve. But now because we have everything in the probability framework, we have a posterior mean for functions, right? For the curve that we fit. From there, we can perform statistical inference using this problem. So that is a lot powerful model than the kernel ridge regression if for the practical purposes.